In this video, we will review absolute extrema, chain rule, and intermediate value theorem. Yesterday, students in class saw problems 3, 4, and 5, which I got from an AP Princeton Review Calculus AB practice book. Let's take a look at how we resolved some of these problems. So, absolute extrema. Let's just remember what this means. If I am looking at any function, if I specify an interval with which I'd like to look at a continuous function, let's say something between a, f of a, and we will say b, f of b. If I'm looking just between this interval, then that means I only am concerning myself with the heights of this function in the region that I've just shaded in. And if you notice, now that we've talked quite a bit in this calculus class about relative min and relative max, here we clearly see what we refer to as a relative minimum, and here we can see a relative max. Now, if the question was, what is the absolute extrema, right? We've already answered that we know there's two local extrema, this relative min here that we've identified, and this relative max that I've just identified. But the question is, between A and B, what's the absolute extrema? Which is really saying, between A and B, what is the greatest and least f of x value or y value? So we're looking for the highest point and the lowest point. And by quick observation, we can note the highest point in that shaded region is going to actually be f of a. And the lowest point, although close, we can see that the relative minimum is actually a little bit lower than the endpoint at b. So we would say our absolute max is at a, f of a, that point. And I don't really know this designated point of this relative minimum because I didn't give it in this problem, but we'll just call it C. So we would say the absolute minimum is C, f of C. Let's leave these notes over here. Now let's try this problem. Alright, so we've got y equals 3 plus 2x squared minus x to the fourth. We're going to set it up by saying check the values at f of 5, f of negative 1. And then I want to check what are called my critical numbers. So first we check endpoints. And that's f of 5 and f of negative 1. And then we're going to check our critical numbers. Now I'm going to let you guys actually solve this, but let's just review what critical numbers are. That would take y prime, which gives me 4x minus 4x cubed, and you're going to set that equal to 0. And if you do that, the values you get for your x are your critical numbers. Alright, so let's say we definitely get a 0, right? So if we plug in 0, we'll get 0. So then I know I'm definitely looking at f of 0. Are there other ways that you can get another value as a critical number? So if we take a look at this, we got 4x minus 4x cubed. We know we can factor out a 4. And we can afford to factor out another x. So that gives us 1 minus x squared, right? So here we got the critical number of 0. And what critical number do we get here? All right, and again, this really is meant for a review. So for you guys to finish this problem, review critical numbers, get your x values, and you should realize pretty quickly that x equals plus or minus 1. Right? So we get critical values of 0, 1, and negative 1. So we're going to check. All right, so to determine the absolute max and the absolute min, you'd plug in each of these values. And as we did in the example shown, determine the highest value, like we did here, and the lowest value. And that's going to be your absolute extrema. All right, let's take a look at the next one, chain rule. So chain rule, I'm just going to go ahead and jump into this one because we've done a lot of chain rule. Chain rule reminder, we have to figure out the dominant function that's sort of leading the way. So another way you want to look at this is through a rewrite. What we're really seeing here is the function sine, whose angle is x squared, is being cubed. So its derivative is going to be 3 sine squared x squared times cosine x squared times 2x. Now let's check and make sure we didn't make a mistake. We have a cubed function. We have the sine function. And we have the angle, which is also a function. And the angle's derivative is 2x. The sine's derivative is cosine, brought the angle with us, x squared. And the original derivative was the cubed function, which became 3 sine squared of x squared. All right, intermediate value theorem. So this is actually a bigger concept to say something quite simple. So the intermediate value theorem is based off of everything we've learned about functions that are continuous. So first of all, let's assume we have a function f of x that is continuous. And we said that anything that's continuous means I can draw that function without picking up my pen or pencil, meaning it has an f value everywhere. We also define continuity as the limit when x approaches any value of c of some function, and that proven limit, which exists, equals the value f of c. All right, so the limit would equal the function value. But this isn't about continuity. So we've got a continuous function. So let's say I've got a continuous function and it looks like this. And we're going to highlight that we're looking at A and B. So between the region A to B, I know I've got f of A. And here we've got f of B. So I'm looking at this function. The intermediate value theorem tells me, right, that if between A and B, I have a change in signs, right, then I can prove, knowing it's continuous, that there must be any value of height in between them. So in this example, it's not as clear that intermediate value theorem could actually be used. So what I'm going to do is choose another A value. And what if instead I'll use the example that A is here, and we'll keep that B. So now I've got this value, and I've got this value. Now let's revisit. I notice that my f of A value is definitely negative. I know my function's continuous, and my f of B value is positive. So I can say that between A and B, so between A and B, since f of A is negative and f of B is positive, I know that f of B is greater than f of A. So I'm writing this inequality, but I also know there must exist some value c in which it goes from negative to positive, meaning it crosses that x-axis, and we call that a 0, right? So intermediate value theorem lets me say, since f of a is less than f of b, and f of a is already negative, I know for a fact there must be some value in the middle, or if I plug in c to get f of c, it will have to be a 0 of the function. Now, in the previous example, I showed a value of a that was over here. And we'll just show it this way. I showed a value of a here and a value of b here. We can use intermediate value theorem here as well, right? Except this is where Rolle's theorem and us talking about the derivative set equal to 0 takes its place, and why we actually learned intermediate value theorem. So intermediate value theorem, we're not doing any calculus. We're just making sure we understand the features of a continuous function. So let's go back to the original problem. The original problem here, we have y equals 2x squared plus x minus 4. What was the question asking, and how can we apply intermediate value theorem now? This question says the intermediate value theorem guarantees a value c such that f of c equals 0, which we just proved, for this function on which of the following intervals? Would it be between -1 and 0? Would it be between 0 and 1, 1 and 2, or 2 and 3? So let's think about that question. It should prove to us that there's some value where we're going to get the 0 of the function, right? So we can go ahead and solve for 2x squared plus x minus 4, find the 0, or find the c, and once we've located the c, we then decide which of these intervals is that c going to be between. So go ahead and try that. Get the 0 of 2x squared plus x minus 4 and tell me which of these options is the correct interval.